Okay, today we're talking about 14 natural logs. We're going to start off reviewing a little bit that you should remember from last year, and then we're going to get into the calculus of it. This is going to be very similar to, it's going to be a continuation of chain rule. A lot of what you're going to do with natural logs is going to require the chain rule to find the derivative. So that's the reason we're doing it at this point. It all ties together. Your next test is going to have a lot of places for you to make mistakes in algebra on it. So it's crucial that you work through the problems and understand what you're doing with those as we go through here. Okay, all of this is stuff that you should remember from, or let me rephrase that. All of this is stuff that you were exposed to when you talked about LNs and E's and exponentials and logarithmic functions last year. These are called the properties of logs. Okay, and these are ways that you can expand a logarithm or condense a logarithm, and it will be very beneficial for us at certain times here. A few things that I want to make note of here. All of this stuff over here, we're not going to be looking at logs, L-O-G. The only thing we look at is Ln, which is the natural log. So you don't really need to be focused on that half there. These two properties right here, you need to memorize. They're going to be on the test. The fact that the Ln of E is 1 and that the Ln of 1 is 0. You just got to memorize those two things. They're going to be expected for you to be able to know on test and on exams. All right? The main properties that you need to remember are these bottom three. Now, all of them could be used, and the others that you're going to use, and it's just going to kind of be intuitive to use those. But the three at the bottom are the ones I want to focus on today. That is the fact that if you've got the Ln of a product, meaning two things being multiplied together, you can break it up as the Ln of the first thing plus the Ln of the second thing. And if you, yes? This is, no, we're talking pre-calculus now. We're talking before calculus, all of this stuff here. If you're taking the natural log of a division problem, it can be the log of the numerator minus the log of the denominator. And if you're taking the log of something to a power, you can bring that power down and make it the coefficient. It's n times the natural log of that. So, yes, it does. It looks kind of like the start of a chain rule. But none of this is calculus. All of this is stuff that you have seen when you were introduced to last year or the year before. So we're going to take just a moment and review some of this. So look at this. If we've got Ln of x times y divided by z squared, how could we expand that out? Okay?
Ln xy minus 2 ln z.
Minus 2 ln z. Grant says that's what it is. What do you think? Connor says we can do ln x plus ln y minus 2 ln z. Is that what you mean, Connor? Okay. All right. Oh, yeah, I should have. It's good practice to keep all of it in parentheses just so you can know what's what. So, that is an expanded. Both of these are expanded form. This bottom one is the most expanded, and that's how you want to be able to get. You want to be able to get to that point. You want to be able to see that I can expand it out to that. And as we work through problems here in just a few minutes, you're going to find out, yes, it's so much easier if I can see it that way. So that's where we're headed to here. Believe it or not, this is going to make finding some derivatives easier because we've got LNs. All right, let's look at the next problem. How can this be expanded? The Ln of root 5x minus 6. 5x minus 6. Okay? Why can't I make that Ln of 5 plus Ln of 6? Yes, all of this is one term. And that's something that after about a few days, you're going to want to start breaking that up. Bless you both times. You can't do addition or subtraction inside the argument. The argument is just saying that we're taking the ln of. If there's addition or subtraction inside the argument, simplify it anymore. That's as expanded as we can get this problem. Okay? So let's look at one more here and tell me what you would do with that. Okay, ln 3x minus ln 4.
Well, ln 3 plus ln 10 minus 9.
Yeah, you could go all the way to that and get it expanded out. And as I said, none of this should just be dusting off some cobwebs of things that you did last year. So let's move on to something new before you get too bored there. That's just you can handle that. I'm not going to worry about that problem here. Now, memorize. Memorize. And this is one I'm just going to say, poof, here it is, okay? We're not going to go through and derive how we got this. The derivative of ln of x is 1 over x. Okay? The terminology you're going to hear me say, the derivative of ln of the argument is 1 over the argument. Now, what does this mean out here? What does this second thing mean? That's right. If we're taking the derivative of something and it's not just x, if it's 2x, if it's 5x, square root of 3x squared plus 7x minus 9, then it's 1 over the argument times the derivative of the argument. That's the way I will normally say it. It's 1 over the argument times the derivative of the argument. Now you can simplify it as u prime over u. That's just the rule for finding the derivative of ln. Memorize and use. It's what we're going to do. So the rest of the time here we're going to work problems to help you memorize that and understand it. How do we find the derivative? Think about it. See if you can write down what you think the derivative is in simplest form of ln 2x. Ways to do this now. An answer they want to share yet? What do you have, Mike?
2 over x, ln 2 over x.
ln 2 over x. All right, I hear 1 over x. I hear, what else did I hear? I heard 2 over 2x, didn't I? I hear 1 over 2x. Okay. Uh-oh, are you amending your answer? All right. Okay. So we've got a lot of different choices for answers here. Let's see what we can come up with, okay? The rule is it's 1 over the argument, which is 2x, times the derivative of the argument. The derivative of the argument is 2, right? So that becomes 2 over 2x, right? And now we can cancel this 2 and this 2, so we simply get 1 over x. Did anybody approach that problem totally different? Yes, ma'am. What did you do? Very good. You said ln 2 plus ln of x. Now that's expanded it. Now how do we take the derivative of that? What's the ln of 2? What's the derivative of ln of 2? Nothing. Why? It's not a variable. This is a constant number. The derivative of ln of 2 is 0. If this is our function, then f prime would be 0 plus 1 over the argument, which is 1 over x. So either way, you got to the same answer. Now the thing that you've got to understand is you've got to take the derivative. You've got to remember to take the derivative. Expanding, that may be useful sometimes, but you still need to be able to take the derivative in the end. So Derivative of this is 1 over x. That would be our final answer. That's just somebody smarter than us has gone through and figured out that that's what the derivative is. So we're just accepting. That's right. We're just accepting on faith that this is what it is.
So it could be any constant and there's still ln of x.
Exactly. ln of 5x would be, the derivative of that would be 1 over x. Okay?
ln
9,000x. ln of pi x would still be, the derivative would be 1 over x. Well, now, here's where we get challenging. So, you got to use a product rule and then take the derivative of the ln and product rule in your head, not too loudly. Yep, FDS plus SDF. First derivative second plus second derivative first. We're on 14. So, all right, first is x times the derivative of ln of x is 1 over x plus second is ln of x times the derivative of first, which is just 1. And x times 1 over x becomes 1 plus ln of x. No. Say that again because what, sir? That's right. This is our derivative at this point in time. If our original function was x ln of x, our derivative is 1 plus ln of x. Okay? And why can't we combine this thing and this thing together? That's not the ln of 1 up there. It's just the number 1, okay? Jacob, all we have learned is that if we're taking if our function is ln of x, then the derivative is 1 over x. That's all we've learned. Yes, this is our derivative, yes. The derivative of ln of x is 1 over x. Okay. Are we comfortable there? Hello, Miss Autumn. How are you today? I didn't want to either, but I showed up. Okay. 1 plus ln of x. Okay. All right. See what you can do with this.
I like that.
Find the derivative. Find. All we have learned, if our function is the ln of x, then our derivative is 1 over x. That's it.
So then you do the chain rule.
There you go. You're doing the chain rule. So it'll be 1 over x cubed plus 1 times the derivative of the argument. 3x squared. Okay. It's 1 over the argument. 1 over the argument times the derivative of the argument. Yes. Yes, you can do derivative over. Yes, that's fine to say that.
Why couldn't they just write it as ln x ln?
Yeah. You thought ln of x cubed plus ln of 1? Okay, because that's a totally different problem there. Then we wouldn't even have to worry about the ln of 1 because the derivative of ln of 1 is very good. Okay. We use the chain rule inside of the ln, okay? So how did you do the product rule? Okay. All right. But do you understand? We've just got the ln of something, so it's 1 over the argument times the derivative of the argument. The argument's what's inside the parentheses. Yes. When you sines and cosines, you may hear me say argument. Argument is the thing that's inside the parentheses. The argument's what's inside the derivative, inside of the ln. The argument sign. The radical sign. Okay. Careful. What's being squared? Go for it. Go for it. Okay. Now, the ln is what's being squared. So we've got to do chain rule. 2 times the ln to the first power times the derivative of ln is 1 over x. So we can get something like 2 ln of x over x for our final answer.
Take that.
I like this better than
One.
I don't really know what we did necessarily.
All right, this, yes, it's over, yep. Now see, because this is, we start off doing chain rule because we've got something to the second power. So the chain rule says it's 2 times that something to the first power times the derivative of this thing. What's the derivative of ln of x? It's just 1 over x.
Yeah, but then you have to put U on the bottom.
But u is x.
Yeah, so but there's already another x. So the U is actually the
Mm-mm. Okay, so what are you wanting to write out here instead of this? Instead of 1 over x, what are you wanting to write out here?
like I'm saying, so see how it's 2 ln x to the top?
Uh-huh.
So it's an understood 1 on the top also.
Yes, there's an understood 1 up there.
There
Yes.
should have been another x on the bottom, so it's 1 over x.
Mm-mm. Because here's our... All right, think of it this way. If we were finding the derivative of u squared, that would be 2 times u times u prime, right? Times whatever the derivative of u is. That's just the chain rule. All right, let's back up. That's right. ln of u, the derivative of that, if that's f, then f prime would be 1 over u, or u prime over u, the way you're saying, right? Okay. Now, this is not the ln of u. This is the ln of x. And this whole thing is being squared. If you're doing this on your calculator, you're going to put x in, find the ln of it, press enter, and then square the answer. You're not squaring the x. All right. Okay, let's chase this a totally different way here, Connor. What's another way to think of ln of x quantity squared? That's the same as ln of x times ln of x, right? All right, so let's take the derivative of this using the product rule. So it's first times derivative of second, 1 over x, plus second, which is ln of x, times the derivative of first, which is 1 over x, right? Now, if I add these two, and we could simplify this to ln of x over x plus ln of x over x, right? No, because if we're using product rule, see, they were multiplying here, but the product rule says first derivative second plus second derivative first. And if we add those two things together, we've got to get two of them in the end. Does that help some? Okay. All right. Now, let's step up our game.
Oh, no.
You can do this the easy way. Somebody figure out the easy way. You already did it? Okay. What'd you do? Are you saying you changed the original function to that?
No,
Okay. So you did this. Well, I don't want to go in there.
What's happening? What did he do?
You did this, okay? All right.
the chain rule and brought that down, and then
When you were taking the derivative, you did the chain rule? Okay. All right, so you said then that's 1 over 3x minus 5 to the 1/2 times, no, you're okay, times the derivative of this, right?
That's 3x.
No, the derivative of 3x minus 5 to the 1/2 is 1/2 3x minus 5 to the negative 1/2 times 3, right? Okay? Now,
Well, you forgot the L1, didn't you?
now what are we going to do? Hold on here. Now what are we going to do? And get 3/2. All right, this is a negative 1/2, so what could we do? If we move it down, then what else could we do? We got 3x minus 5 to the 1/2. We got two of those, don't we? So we get 3/2 over 3x minus 5. Right?
where did we get here then?
Yeah.
We had one of them here. And then this negative 1/2 we brought down. Okay? Yes, there's an easier way to do it. Okay. So now, this is fine. There's nothing wrong with this. All of Mary Catherine's math is right there. Perfect. Because we took the derivative. When we take the derivative, the ln goes away. All right. This is what I want to do with this problem, okay? I want to do paste. Where's paste? Okay. Here's what I'm going to do. Change this using your properties of exponents. Now, as Mary Catherine said, we could write this as ln of 3x minus 5 to the 1/2. But with our properties of exponents, we could also remember that power property at the very bottom. We could bring the 1/2 out in front. Not taking the derivative now. We're just taking the 1/2 out in front. And this is the same function. So this function here is equivalent to what we started with back there. We haven't done any calculus yet. We've just made our calculus. Because now we're going to take the derivative of this thing out here. Well, we know our answer's got a 1/2 in it, so I'm going to write the 1/2 times. We're taking the derivative of ln of 3x minus 5. What's the derivative of ln? 1 over the argument times, which is 3.
Oh my God.
3 over 2 parentheses 3x minus 5. Now, there's nothing wrong with what she was doing, but when we problems like we're going to give you, that's something you need to understand. Sometimes it's easier to expand and then take the derivative. Expand and then take the derivative. For example, right here, it will take you days. Exactly. So don't do all of that. Expand it out to begin with. How can we expand this out? All right, does everybody see how I did what Sam said do there?
Where's the x?
The ln of x right here plus, bring this 3 down, 3 times the ln of x squared minus 5. That's all my numerator. Minus, what am I going to do? 1/2 ln of all of that mess. Now taking the derivative, that's the hard part right there. Expanding all that out. Now taking the derivative is easy. Okay. We're going to take this problem here and we're going to expand it out using our properties of logarithms, that first page we saw. So I see a division sign, so I can say that's ln of x, ln of the numerator minus ln of the denominator. All right? You with me there, Connor? Okay. We're using this division property right here. Okay? So now that we've got that done, now let's go back and look at just the first part of our statement here, Connor. We've got x times something. That's the multiplication one. So we can break this part up as ln of x plus ln of x squared minus 5 cubed. And we're just going to bring this down over here. Well, we've got powers there. If we go down and use the power property, we can bring these powers down right here and make them coefficients. And we get the ln of x plus 3 ln of x squared minus 5 minus 1/2 ln of 5x to the 4th minus 3x. I used the power property and brought the power down on each one of them. That's right, and that's the hard part for y'all to get across here. We haven't started the problem yet. We haven't even started the problem. We've made the problem into something far easier to do now. Because now you can look at these and fairly easily tell what the derivative is going to be. This is still our function right here. This is still f. To get f prime, what's the derivative of ln of x? 1 over x. Plus, we know that's going to have a 3 because it's 3 times that. The derivative of ln of x squared minus 5 is 1 over x squared minus 5, 1 over the argument, times, not 3, not 2, 2x. Because the derivative of x squared is 2x. Remember, but u is anything that's not x in there. Or anything other than x. This isn't x, this is x squared minus 5. Just x, yes. If there's just an x in there, then it's 1 over x. If it's something other than that, then you think of it as a u. It should have been, yeah. Okay. Minus. We know it's a 1/2. What's the derivative of this? Again, it's 1 over the argument times the derivative of that, 20x cubed minus 3. This is times 2x because it's 1 over the argument, 1 over x squared minus 5 times the derivative of x squared minus 5. The derivative of x squared minus 5 is 2x. That's right, we have to do chain rule on each one. And now we get 1 over x plus 6x over x squared minus 5 minus 20x cubed minus 3 over 2 times 5x to the fourth minus 3x. Yes, I would say let's leave it like that. We could do smiling x a couple of times and add them together, but that would be painful. Oh. Okay. This 2, yes. Yes. You could distribute and have 10x to the fourth minus 6x if you wanted to. Woo! See how much fun this can become? All right. I want to see how many more of these I want to do.
No. Okay. Dude, I'm gonna keep this just because I need something to accent my list. What?
Okay.
I want to record. Go back.
Sure.
You weren't there. You don't know.
All right. Are we comfortable there yet?
Yes.
We're kind of sort of comfortable here. It's not the end of the world.
I forgot the meaning of the word comfortable when I started.
That's good.
That means like fun.
The meaning of what?
Fun.
Oh, this is all fun. Come on now. No. Okay. How do we do this? What's the problem with this problem? Value bars kind of can mess with us there. Okay, let's kind of forget about the absolute value bars for a minute and just treat it like it is there. Okay, so find the derivative of that just like it is. Okay, so f prime is 1 over cosine times negative sine, which is that's where we're going with it. Okay.
What does absolute value do? I've never.
It makes whatever the answer is positive. It makes whatever the answer of this is positive. Okay? It's not going to affect our derivative. That's the way we're going to approach it right now. Okay? All right, now I want to show you one more problem and show you the great benefit of this. Okay? So let's see if we can let's say y equals let's just do something real ugly. X squared parentheses x cubed plus 4 cubed over the square root of 2x plus 5. Okay? I've just made that up off the top of my head here. What's the problem with finding the derivative of that? We've got product rule up here, and then Lodi high. But when we do the product rule, we've got the chain rule in here, don't we? And then when we do Lodi high, we're going to do the chain rule, aren't we? So it's just going to take a lot of effort to get there, okay? Now, do y'all remember one of the first things you ever learned about equations is if you do something on this side, do it to the other side, right? As long as you do the same thing to both sides. So look at what we're going to do. We're going to change this and make it the ln of y equals the ln of x squared. Whoops, not plus. I like that purple there. X cubed plus 4 cubed. Now, is it legal to do that?
Yeah, perfectly legal.
We did the same thing on both sides, so it must be legal. Okay. Now, how does that help? Watch this. We can make this now. ln of y equals 2 ln x plus 3 Okay, that's just expanding out using our properties, right? Still haven't done any calculus yet, have we? Oops, didn't want to do that. Now what do we need to do? If our goal is to find the derivative. All right, now we need to take the derivative. Well, I want you to start over here. What's the derivative of ln of y? 1 over y times y prime. What's that called that you just did there? Yeah? Something that you were working on, implicit differentiation? Okay. 1 over y times y prime. Then we can go through and do all of this stuff over here. 2 over x plus 9x squared over x cubed plus 4 minus... I just did a bunch in my head, okay? You need to get there. You're smart enough to get there. Yeah, you are. You're taking the derivative of everything. What's the derivative of ln of that? 3x squared over x cubed plus 4, right? And what's 3 times 3x squared? See? You're smarter than you thought. You just get freaked out when I blow your mind that way.
Wouldn't you do 2 times 3x?
Here? All right, but what's the derivative of 2x plus 5? And that 2 will cancel with that 2 down there. You're saying I want a 2 out here in front, but then you'd have a 2 up here and you could cancel those out. All right? But now, I don't want y in my answer. I don't want y in my answer. And I've got 1 over y over here. So if I multiply both sides by y, then I've got y prime is all of this math times y. Listen to the statement. I don't want y in my answer. You can get it wrong. That is a 2 that was canceled. Okay. I don't want y in my answer. It's so easy as staring you in the face. Nope. I don't want y in my answer. So how do I do what I do?
Derive again.
I don't want y in my answer.
F of x.
I've already, nope. If I do that, then I put y back over here. I don't want y in my answer. What do you mean? I don't want f of it. I want nothing but x's in there. What's y equal to?
You just plug that into y.
What if I put that in place of y? Do I have y in my answer anymore?
No, it's going to be all messy again.
Oh, no. You leave all of this mess times whatever that y was up there. I don't even remember what it was there. That's a little trick that's going to make taking derivatives far easier sometimes for you, okay? If the directions say use logarithmic differentiation, that's a fancy way of saying do this. Introduce LNs. If the directions say use logarithmic differentiation, it's a fancy way of saying do this.
So we can, what's that? WY time.
Okay. You have the remainder of our time today to work on the your turn problems here. Do you have any problems behind this that you need to get? No, we did implicit yesterday. You can work on this. You've got a WebAssign on implicit due Monday, a WebAssign on LNs due Tuesday. We're going to talk about some physics tomorrow. We'll talk about E's sometime next week, and we'll have a test probably early the week after that.
Yeah.
Early the week after that. That's my goal right now, okay?